Okay, this is going to be a short lecture, but I'm going to do a lot of hand waving, so to speak. You won't actually see my hands waving, but you'll hear it in my voice, I think. Um, uh, this is, and although it's short, it's rather important. It really gives a deep insight into how the various methods that we'll look at of approximating solutions to ODEs, how they actually compare with one another in terms of their numerical efficiency. Okay, so this is asymptotic and error analysis. That is, we're going to find a formula for error which is not exactly accurate, but it does approach exactness in the limit as h goes to 0. Right? That's what we mean by an asymptotic error. So we're looking at the error En between the our value yn, which is the approximation we got for the solution at the point xn, and the true value of the solution at xn, capital Y of xn. So capital Y represents the true solution to the problem. Okay, so En is the difference between the two. Now what we want to look at is how En changes from one iteration to the next, from n to n plus 1, as we go to the next x and y values. And we, in particular, we want to look at how the error can be broken down into the propagated error, which is the error that's inherited from the previous step, and the truncation error, which is the new error that's introduced at the new step. So, using the Euler method, the formula for yn plus 1 is very simple. You simply take yn, the previous y value, and add h times the value of f at the old point, the previous point xn, yn. Okay. Now, there's immediately you can see there's some sources of propagated error here. Because yn was not exactly equal to the exact value y of xn, the difference between these two is exactly going to be this guy, en, right? So we immediately get some inherited error because we're starting with an incorrect value for yn, and that inherited error is en. In addition, we also, because we're using the wrong value of yn, we're getting the wrong value of f of x and y, right? And the difference is pretty close to, well, whatever the change in y is, times the y derivative of f, evaluated at some point. Again, here we're using a mean value version of the mean value theorem. We can say that the actual error in the value of y is equal to delta y times fy evaluated at some point c1. And of course, delta y here is exactly en, right? That's exactly en because it's the difference between the true value of y and the value we're using, which is yn. So therefore, we get this term. We get h times, or rather the error in this is now going to be h times this quantity. So h times delta y times fy at xn c1. So that's another term in the inherited error, right, or the propagated error. Finally, we also have the new error that's introduced now called the truncation error, and that arises because the solution y is not actually a straight line, so we cannot exactly calculate yn using this formula, right? It's not going to be exactly equal to the old yn plus h times some slope because this is not a straight line. Its slope is not constant. So because y prime varies, this will not give us the correct value, and therefore we have to add a second order term from the Taylor series in order to correct for the fact that the true solution is not linear, right? So we have this is exactly the second order error term from the Taylor series expansion of the solution y. It simply represents the error in the linear expression for y. So that's the truncation error. That's the new error that's introduced. So if you look at the whole thing altogether, from the first two terms, we can factor out En, so we get this. And that all represents the propagated or inherited error. And then we have the new error, or the truncation error, which is this term. And that is going to be the error at stage n+1. And you can find this in the book. It's actually equation 8.30 in the textbook. So it shows you how to break down the error at stage n+1 into the propagated error, the error from the previous stage, and the new error that's introduced. Now, an important aspect of this is that if you want to know how the error behaves, the total error behaves, that is, does it behave like h or like h squared or some higher order of h? That is really going to be determined by the truncation error here, because the inherited error will just continue to behave as it did at the previous step. So as long as, if we know that the previously En was behaving proportional to h, then En+1 will also be behaving proportional to h, or at least this term will. So this term we don't have to worry about because it's inherited from the previous error. It will continue to behave as the previous error did. But we have to make sure that the new error that's introduced also behaves in the same way, of order h or of order h squared or whatever. So now what we have to do is look more carefully at this truncation error term and see how that behaves as h gets smaller. Okay, so here I just copied that truncation error term over, and now we want to see what happens if you were to, say, cut h in half. That would mean that you'd take the interval from xn to xn+1 and you'd split it in two. So we'd introduce the midpoint m halfway between xn and n+1, and we'd actually split this up into two intervals, one from xn to m and one from n to xn+1. Now, on both of the two smaller subintervals, we can use this truncation error formula as long as we reduce h but to h over 2. So that's what I did here. On each of the smaller subintervals, the error is going to be h over 2 squared over 2, and then times y prime evaluated at some point c. By the way, now these are two slightly different intervals, so technically the c would not be the same on both of them. But once again, we can appeal to the integral form of the mean value theorem and say that it's actually going to, we can actually pick a single c that'll give us the overall correct value for both of them. And then, of course, we did that twice, so we have to multiply that by 2, right? We had two subintervals. Simplifying, we get this expression. And if you compare now the original error in interval h and the new error on the same interval, but having broken it up into two subintervals of size h over 2, we find that reducing the size of h reduces the error by 1/2. Instead of having h squared over 2, now we've got h squared over 4. So we've reduced the error by a factor of 1/2. Right, so the summary is that, let me do this. The summary is that if we reduce h to h over 2, we also reduce the error by 1/2. And so this demonstrates that the overall error is going to be proportional to h. That is because the truncation error is proportional to h, right? The error is affected by the same factor that we changed h by. As I said on the previous page, as long as the truncation error behaves in a certain way, the inherited or propagated error will also behave in that way. So we can say in this case, using the Euler formula, that it is indeed true, something I mentioned earlier, that the overall error is proportional to h. And when we cut h in half, we'll cut the error in half at all points along the evolution of the curve. Now that doesn't mean the error is equal at all points. So to state this more precisely, if you look in the book, this is equation 8.38 in the textbook. It's a more precise statement of this. It says that when h is small, when h is small, the error in y at some point x is proportional to h. Now dx here, that's the constant of proportionality, And I wrote d sub x because this constant of proportionality depends on what x is, right? So for some x, this may be large. For some x, this may be small. But for all x's, there'll be some constant dx such that the error behaves like dx times h. Another way to put it, we could say that for each x in the interval on which we're working from x0 to b, there is some constant d such that when you divide the error by h, the limit is going to be d as h goes to 0. Right? So the ratio between the error and h approaches some fixed constant in the limit. Okay, with these results, now that we know that the error is in fact proportional to h, we can apply a Richardson extrapolation. I think we've seen this in several contexts already. So just to simplify the notation, in this case, our estimates y, they're actually going to depend on two things. They're going to depend on k, which is which step of the iteration we're looking at, whether we're looking at x, x1 or x2 or x13 or x123. So that's what k is. And it's also going to depend on h, right? What h we're using to break down the interval into subintervals. Right? So I'm going to simplify that. I'm just going to write yh. So I'm going to say we're looking at a particular y value that corresponds to a particular x value, and we're changing the h value and seeing what happens. Okay, so according to what we did on the previous page, we know that at any particular x value, the true y value minus the estimated y value using a particular value of h, that's the error, will be proportional, will be approximately equal to d times h, right? It'll be proportional to h in the limit, right? So this is only an approximate equality, but it should be pretty good when h is small. And then if we cut h in two, then we get this, that the error or the difference between the true value and the approximation when we use an h value of h over 2 is approximately d times h over 2. Now, multiply the second equation through by 2, and then the two right-hand sides are equal. Therefore, the two left-hand sides are equal. So we get this. We get that y minus yh is equal to twice y minus yh over 2. Now there's two useful ways to solve this equation. We can just solve for y, and this gives us Richardson's extrapolation. That is, oops, what have I done? That is, oh yeah, sorry. That is, this gives us a better estimate for y. I mean, assuming that, if we know, given the progress from yh to yh over 2, we can make a prediction about what the ultimate true value of y is going to be, right? A more accurate prediction than just using yh over 2. So you solve it, you get this. Again, it's a kind of a weighted average of the two recent estimates for y. So we count the new estimate twice and we subtract off the old estimate, right? So we're actually counting the old estimate a negative number of times. Another useful way to solve this equation is to just get a more accurate, or to get some idea of the error, reasonably accurate estimate of the current error using h over 2. And very simple, it says that the error in the estimate using h over 2 is approximately equal to the difference between the previous approximation and the new one, right? And so I was kind of appealing to that in a sense when I was looking at the graph the other day and showing the estimates for the different h values, and that turns out to be a valid reasoning, that in fact the true error is approximately equal to the difference in the two most recent approximations when you divide h by 2. Okay, so that's all I have to do today, but it's very important because we'll be able to use this kind of analysis to show why other methods for doing numerical ODEs, for solving ODEs numerically, give better results and converge to the true solution faster. So that'll be the next lecture, slightly better methods than the naive Euler method.